Luca Congedo and you're watching from JS Remote Sensing. In this video tutorial we're going to use several tools of the semi-automatic classification plugin for assessing length over change. In particular, we are going to use post-processing tools such as reclassification, direct editing, that will allow us to analyze length over change and relate this with land use. So let's zoom in. So the first step is the refinement of the classification. We can first load the classifications that we have downloaded. In this case, the imperviousness density from the Copernicus services. Here we have the imperviousness density 2012 and 2015. Here we have the imperviousness density that represents the percentage of built-up area inside the pixel. This raster has 20-meter resolution. This is a clipped area over the beautiful city of Florence in Italy. For photo interpretation, we should also load high-resolution images. In this case, I've prepared the Landsat 8 image. Here, we can load this in QGIS. And we can see the city of Florence here. All these Landsat bands will be useful for photo interpretation. So first we are going to create a bandset from the SCP menu bandset here. We click the refresh button. For the refinement we need to define a bandset 1 with the imperviousness density 2012. We click add. Here, as you can see, this is the imperviousness density 2012. We can also add a second bandset where we load the Landsat bands that will be used for photo interpretation. Here we select all the bands and we click add. These are the Landsat bands and we are going to set the center wavelength here. So now we can use the Landsat bands for displaying a color composite, a false color composite or a natural color composite. So here we have the image that we are going to use for photo interpretation. For the refinement, here we move to the top this layer. Here we have the imperviousness density of 2012 and we are going to edit this raster. But first, you should set the active bandset 1. This is particularly important to set the active bandset the same as the raster we are going to edit. Then we go to SCP menu Post-Processing and open the Edit Raster tool. We click Refresh and select the input raster, the imperviousness density 2012. Then in the working toolbar we activate the ROI, the manual ROI tool. For instance, we can correct the raster, the classification here in this area. We have these white pixels, these white patches of built-up that are classified with a value 0 in the raster. So we can here create a ROI covering these pixels. Here. Then in the edit raster we set the option use constant value and we enter the value that we want, for instance 100, and we click run. And here the raster is edited. Sometimes you need to zoom in and zoom out to refresh the view. As you can see, all the pixels are classified with a value of 100. Of course, we can repeat the process for the imperviousness density of 2015. Here. We just need to change the input raster in the edit tool here. We don't need to create the ROI again. As you can see, it's already there. Also the constant value has been set. Then we click Run. And as you can see, we zoom in and zoom out. Here, all the pixels also of the impervious density 2015 have been replaced with the value 100. Of course, we can repeat these steps, correcting also other errors and changing the values of the raster. Another useful step is to report the area and the proportion of each class. So we can use this tool, the SCP menu, post-processing tool, classification report. Here we select the classification, for instance the impervious density 2012, and we save the report here, the text file. So here, for instance, report 2012. And here we have the report with all the classes. So the imperviousness density with the pixel sum, the percentage of the classification, and the area in square meters. Of course, we can repeat the same step for the imperviousness density 2015. Click Run, we save this report to another text file. Here we have also the report for the other classification. So now that we are going to calculate the length over change, we must first reclassify the raster. So the imperviousness density, which is a percentage, will be reclassified to a built-up raster. So from the SCP menu, post-processing reclassification tool, here we select the input, the imperviousness density 2012. We are going to enter here the expression, the old value, and the new value of the reclassification. We can add a row, a new rule here. So we have the two rows, and we enter the expression raster lower than 30, which is the not built up. The other expression raster greater or equal than 30, which is built up. And we enter the new value 1 that represents built up. We uncheck this option here and we click Run. We select where to save the reclassified raster, for instance BU 2012. And here we have the reclassified raster, so the built up with the value 1. We can display a better symbology for this raster. So white for the not built up and red for the built up. Here we have this reclassified raster 2012. We can compare this raster, as you can see, with the Landsat image. Now we repeat the same reclassification for the imperviousness density 2015. We can leave the same settings here and click Run. Now we select where to save the 2015 raster here. We can copy the style and paste the style to the new built-up raster. And so here we have the 2015 and 2012 built-up rasters. As you can see, there are very few changes. For instance, if we zoom here, we can see a few pixels, a few new built-up area from 2012 and 2015. The next step is to remove isolated pixels. As you can see here, there are a few pixels that can be, for instance, classification errors. So sometimes it is useful to remove these pixels. So we open the SCP menu, Post-Processing, and we click Classification Sieve. In this tool we just need to select the classification input. So we need to change the input here. We select the built-up raster, the reclassified raster, and here we can enter the size threshold for removing isolated pixels. In this case we leave 2, but of course we can increase the number of pixels here. We can also change the pixel connection, which is the rule for selecting pixels in a moving window, and then we click Run. We have here the built-up 2012 sieve. As you can see, isolated pixels are removed. Here, as you can see, there are no single pixels. Of course, we can repeat the same steps for the 2015 raster, or built-up raster, here. So we open the same tool, Classification Sieve, and select built-up 2015 with the same settings, and we click Run. And we save it as built-up 2015 sieve. As you can see, isolated pixels are removed also for the non-built-up class. Now that we have refined the classifications, we can assess length cover change. So we're going to assess length cover change between the 2012 and 2015 classifications. From the SCP menu Post-Processing, we select length cover change. Click here Refresh. And we select as a reference classification the built-up 2012 sieve here. And for the new classification we select the built-up 2015 sieve. We uncheck this option, report and changed pixels, because we only want the changed pixels. Then we click Run and select the output. After the process, we have here the report of the length cover change. We can see here that from reference 0 to new class 1 we have 520 pixels, and we have no pixels from 1 to 0. We can zoom here over the change raster. This is a change occurred between 2012 and 2015. You can see here from the Landsat image, and these are all the changes, 520 pixels. So now it is very interesting to analyze the context of length cover change. So we can open the Corinne length cover data, the Copernicus Corinne length cover. We can load here this vector, which is the Corinne length cover 2012. Here we have the first level class. If we open the attribute table here, we can see the attributes, so the 3-level code. And here we have this field, class 1, which is the first level code. The first level code that I have already added to the attribute table here. We are going to use this code for assessing the context of length cover change. So we go to the SCP menu, Post-Processing, Cross-Classification. Here, in this tool, we select the classification. In particular, we select the change raster here. We need to check the useNode data value here, because we don't need to report the unchanged pixels. As you can see here, the change raster has value 0 for unchanged pixels. And then we select the reference vector, we click refresh, and select the Corine cover 2012. And we select class 1 as vector field, the class of the first level of Corine cover. Then we click run and select the output of this comparison. So for instance, change CLC and click save. After the processing, we have the output, which is this change CLC raster, where each value represents a combination between the reference, the Corine cover, and the classification. Of course, we have also the pixel sum in the area in square meters. And here we have the cross matrix with the comparison between the changes with value 1 here and each class of the Corine cover. So here for the changes we have for the class 1 the Corine cover artificial, we have 157,000 square meters of changes, of built-up changes inside the artificial areas. And so on also for the other classes, and of course we have also the total area. Now that we have calculated the context of length cover change, we can also calculate the spectral signatures of each length cover change. For instance, we can use this raster, change Corine length cover. Using this Landsat image here, defined in Landsat 2, we can calculate the spectral signatures, but first we need to create a training input here, where spectral signatures will be saved. So click New Training Input and save the signatures file. Then in the SCP menu, Post-Processing, we select the class signature. Here we click Refresh button and we select Change Corine cover raster here. We need to define the bandset, the bandset 2, which is the bandset where Landsat images were saved. Here, so we set the bandset 2, and we check, of course, Save Resulting Signatures to Signature List. Then we click Run, and select the output file. Also, a signature output will be created. Here we have the signature output with the values of each signature. Inside the training input we have here the signatures. Of course, the macro class 0 represents unchanged pixels, so we are not interested in this. We select these three signatures here and we can display the spectral plot. As you can see here, these are the spectral signatures of changes in the context of the Corine cover class 1, class 2 and class 3. So, for instance, we could use these spectral signatures for creating a new classification or updating the classification raster. As final step, we can convert the classification raster, the length cover change raster, to vector. So in the CP menu, Post-Processing, Classification to Vector. Here in this tool, we can select the change raster, the change CLC raster. We uncheck this option and we click Run. We save the output vector file, for instance change vector. we click Save. After a while, the change vector is loaded, as you can see here. If we open the attribute table, we can see here in this field the value of the change. So here, for instance, this value 1 is a change in the Greenland cover class 1. Here, this is another change. So this change occurred in agricultural areas, according to the Greenland cover. So of course we can edit this vector. For instance, we can remove the unchanged area that has value 0. If we select this feature, we can edit the vector and remove this feature representing unchanged area. And we can save it. So we just have the polygons of changes here. And these are the changes occurred between 2012 and 2015 according to the imperviousness density raster that we have reclassified and that we have compared to Greenland cover. So in this tutorial we have used several tools for analyzing land cover change. If you have comments or questions, please join the Facebook group of the Semi-Automatic Classification plugin. Thank you for watching.